Greetings everyone, and welcome to this video on plots for binary classification and the diagnosticity of a test. Building on the previous videos, after we select the check boxes for the plots we want, we should have something that looks like this. The probability positive plot is essentially a bar chart that conveys to the users that the probability of a positive condition, for example in this case hypercholesterolemia, given the test result outcome, positive or negative, the baseline rate and the test characteristics, which are sensitivity and specificity. The icon plot aids understanding by showing particular numbers of people being healthy, infected, diagnosed positively, and diagnosed negatively. In the real world, we do not have perfect tests. Maximizing sensitivity and specificity at the same time is constrained, as they are inversely related. Increasing sensitivity comes at the cost of decreasing specificity and vice versa. We may imagine this as a moving threshold that defined what is considered a positive and negative case. If we set the threshold leniently, we can detect more true positive cases, but at the cost of polluting the pool of positive test results and false positives. The ROC curve, or receiver operating characteristic curve, illustrates the diagnostic ability of a binary classifier when this threshold is varied. That is, it shows the trade-off between sensitivity and specificity. In this example, we imagine that the two subpopulations that are positive and negative cases be distributed as two normal distributions. The difference between the location of the two distributions determines how well these subpopulations are separated and thus easy to classify. We then imagine moving the test threshold from left to right and recording the 1 minus specificity as seen right here on the x-axis and sensitivity on the y-axis. A perfect test would be so good at discriminating between positive and negative cases that there would be no trade-off, and the plot would just show a single dot in the upper left corner. If the test were essentially useless at discriminating between positive and negative cases, we would see a perfect trade-off displayed in the plot as a diagonal line. The figure shows that our ROC lies somewhere in between these two extremes. The actual location of the test at hand, which is sensitivity of 0.73 and specificity of 0.78, as indicated by the gray dot as seen right here in the ROC curve, with the dashed line denoting 95% credible intervals. In the test characteristics by threshold graph, a similar demonstration of the trade-off between sensitivity and specificity is seen when they are plotted as a function of the test threshold. In this case, a threshold cholesterol level of 200 milligrams per deciliter. The graph conveys that when the test is more conservative, that is, we have a high threshold, specificity increases, but sensitivity decreases and vice versa. Coming to the PPV and NPV by prevalence plot, this plot shows how both of these values change as a function of prevalence when the test characteristics are kept constant. In this example, since our prevalence is 0.491, we are able to see the PPV and NPV at this point, both of which are approximately 0.75. The alluvial plot provides us with another visualization that offers insight into the true positive, true negative, false positive and false negative values. And we can see that in our plot there is approximately a 1:1 correspondence between the proportion of positive cases, as you can see right here. Hence, if one overestimated prevalence of hypercholesterolemia using the proportion of positive test results at face value, it would yield a prevalence estimate of approximately 50%, which is close to the true prevalence. Coming to the last plot, which is arguably one of the most important plots, this is the estimates plot, which displays the point values of the data chosen with their 95% credible intervals right here. Thus, we get a visual representation of the uncertainty of these values too. That's it for this video. Thanks for watching, and I'll see you in the next